For instance, to find a good hydrocarbon play, geologists start by looking for sedimentary basins, where there is sedimentary rock. The yellow and orange areas on this map demonstrate sedimentary basins. The brown color symbolizes known areas of oil. In this study, the geologists have colored the map to show that the Middle East is a sedimentary basin with large oil deposits. Now, let's go back to the larger map and look at the sedimentary basins where some of the large oil fields have been found. Here you can see the location of sedimentary basins containing some of the world's largest oil reserves. These large oil fields are located here in Russia, in the Gulf of Mexico, Alaska, Canada, the North Sea, the Middle East, Africa, and Venezuela. They know there is oil there, so they continue to explore the region for new fields, some even hidden below existing fields. In addition, geologists and geoscientists use what is known as a process of elimination. In preparing their data, they look for reasons why an area can be excluded. For instance, they keep track of regions where it may be too dangerous to drill, or areas where the rigs could not get permission to enter and drill. Political and non-geological reasons help eliminate large areas of the Earth's surface that is not open to oil companies to drill. In any event, once the geologists and geoscientists have exhausted all the ways where they can acquire data from the surface, they turn their attention to the subsurface. Here, they must rely on other types of tools and instruments to help them visualize what is down below in the subsurface. Of course, they won't actually be able to see into the subsurface, but their tools will allow them to gather data that will enable them to plot the structures, rock types, and presence of fluids in the subsurface. There are three basic tools that they use in the subsurface to acquire data. They are the gravity meter, the magnetic meter, and the seismic survey. Surprisingly, the technology used in these tools were perfected many years ago. Even so, this technology is still widely used today. Why? Because the technology used in these three tools still allow the petroleum geoscientists to envision the big picture of underground structures. The gravity meter measures the Earth's gravity. The second, the magnetic meter, measures the Earth's magnetic field. The third, the seismic survey, measures sound waves, refracting and reflecting off different layers of rock. Now let's look at each in more detail. The gravity meter first measures the changes in rock density in the subsurface. The standard acceleration gravity constant, G, was first developed by Isaac Newton in the 17th century. Today, scientists have precisely calculated G to equal 9.80665 meters per second squared. G represents the gravitational constant of the entire Earth. However, small deviations from this number can be measured at the surface of the planet using a gravity meter. It indicates small variations in the rock density below. The last number, 5, for example, can vary between plus and minus 5 digits depending on the density of the rock below. This allows the geologist to measure density changes. Let me explain why this is important. To get G, or the gravity constant of a local area, a gravity meter is put on the ground to measure whether the subsurface has a high or low density. Igneous and metamorphic rocks have slightly higher densities than the average density of the Earth. So when igneous and metamorphic rocks are present, they will measure a slightly larger G reading. With sedimentary rock, the meter will measure a slightly lower G than the average G of the Earth. By taking several measurements over an area on the surface of the Earth, petroleum geoscientists can begin to construct maps illustrating the positions of the different rock types below. They then plot this data on a grid, making contour maps like these. High Gs are usually colored red, indicating hard or high-density rock structures. Low-density rock, or sedimentary rock, is usually colored blue. It is these sedimentary rock formations and basins in blue that the geologist is interested in. Of course, this data isn't very accurate for specific locations, but it can give the geologist a fairly accurate big picture of a large area. It allows the geologist and the geoscientist to eliminate areas of igneous and metamorphic rock and concentrate on the large areas where there are sedimentary basins, where oil and gas may have accumulated. The second tool, the magnetic meter, has a compass that points to magnetic north. Within the Earth, we find large deposits of igneous rocks made up of iron or magnesium. These large structures can be very magnetic, which allows the magnetic meter to deflect slightly from true north. By identifying these smaller magnetic fields, the magnetic meter, like the gravity meter, allows the geoscientist to use the recorded measurements over a large area to build contour maps like these to illustrate the presence of small magnetic variations. Areas of high magnetic variations are colored red, and those with low magnetic variations are colored green. The red areas are associated with igneous rocks, and the green areas are associated with sedimentary basins. This is another example of how geoscientists use the process of elimination. They eliminate the areas of igneous rocks from further exploration considerations. These tools, while useful to view the big picture, can only suggest where to look further. More detailed data is still needed to determine if the sedimentary basins contain traps and hydrocarbon accumulations. Here are some examples of models of computer-generated maps of formations that contain different structures like anticlines and faults with their depths and heights. By also studying contour maps, you can see what is called the cross profile of a structure underground. It is what you might see if you could cut into the surface, like you would a layer cake. Here you can see what looks like a mountain underground. These negative numbers indicate that you are below the surface. Here you can see what might be an anticline. Using powerful computer tools, you can rotate the 2D and 3D visual contour maps to look at structures from different directions and angles, from the top to the bottom, from any perspective. What we are looking for is closure. Do any of these traps have that closure?